Hi everyone, my name is Paulo Souza, and today I'll give you an overview of some of the AI features that come with the Unreal Engine. To demonstrate that, we've built this very simple stealth game, and we're going to use that as a basis for our enemy AI. We've built some visual features in this actor, like the laser light effects you're seeing. Those will serve as a visual cue to the player, representing the enemy's visual cone and the current AI state. We have also built an actor that can be thrown, like a rock. We're going to use this to demonstrate how to make the AI aware to noises. Without that said, let's start. Creating AI in Unreal is facilitated by the Gameplay Framework, a built-in set of features that helps organizing the logic and interaction between entities in your application. For us to understand the AI framework in Unreal, we need to understand the relationship between pawns and controllers. A pawn is a type of actor that can be an agent in the world, and every pawn can be possessed by a controller. The pawn is the body in our analogy, and if the pawn is the physical representation of an agent in the world, then the controller class will be the soul, where we can set rules for the pawn's behavior. Continuing that analogy, then the behavior tree, which usually runs inside a controller, would be the brain, the object that actually makes the decisions and command the controller to do things. And finally, the black parts exist to support the behavior tree with data it can use to make decisions. The blackboard serves as the brain's memory in our analogy. Let's continue to set up our pawn to have an AI controller and create our first behavior tree. Before we start, we'll make sure our enemy pawn has a pre-configured AI controller class. We're going to use a clean AI controller blueprint for this. Then, we're going to create our first behavior tree, which we're calling EnemyBT. After that, we are ready to configure our AI controller to run that behavior tree we have just created. Double-click our behavior tree, and we're ready to start. But what is really a behavior tree? Behavior tree is a model that describes switchings between a finite set of tasks that allow developers to create very complex logic composed of these simple tasks. It's built as a hierarchical set of nodes that control the flow of decision-making of an AI entity. It's very easy to expand without worrying how simple the tasks are implemented. It's also easier to understand in code, it's very easy to debug, and it's widely used across the industry, and that's why we're going to talk about this here. You will usually find four types of elements in a behavior tree: composites, decorators, services, or tasks. Composites define the root of the branch and the base rules of how that branch is executed. Decorators are also known as conditionals. They define whether or not a branch in a tree or even a single node can be executed. Services will execute at their defined frequency as long as the branch is being executed. And tasks, which are the nodes that actually do things, they can have decorators or services attached to them too. It's very important for you to understand how the execution flow of BTs work. BT branches are executed in order, from the top to the bottom at the higher level, and from the left to the right at the branch level, which means that branches to the left have execution priority over the branches to the right. That's important to understand before we can start organizing our decision-making tree. It's also very important for you to understand the difference between composites, sequence, and selector. A sequence composite executes every child or branch in order until one of them fails. A selector composite finds and executes the first child that does not fail. What it does, it makes sequence composites very useful when you want to execute a list of tasks one after the other, but need that the entire branch of tasks to be cancelled if one of the tasks fail. The selector, meanwhile, are more useful when you need to make a decision and select which task or branch you want to execute based on, let's say, a set of parameters. We're going to make it much easier to understand once we start demoing this. So let's do it. Let's start by adding a sequence node. From root, only composite nodes can be added. After that, we're going to add 3 tasks by copying and pasting it and connecting to our sequence composite node. As we said before, you can see that we have 3 tasks that are executed in order, one after the other. Let's then select one of the tasks and add a decorator that forces it to fail. And what we're seeing here is that since the second task in that branch fails during execution, the entire sequence node is aborted and none of the tasks to the right are ever going to be executed. Okay, but what if we change to a selector composite? Well, what we can see is that it's only executing the first task. As we mentioned before, the selector composite finds and executes the first child in the branch that doesn't fail. And what if we change the order of the nodes? As we mentioned, branches execute from the left to the right. And if we mouse over the circles on the task nodes, you can see the execution index of these tasks, or the order of the execution. And if we play the game, you can see that since the first task will always fail, the selector composite actually tries to execute the next child. So let's start building our AI. We will create a sequence node and add a few actions, like wait and move to tasks. If we play the game as it is now, our move to task will always fail, because this task specifically needs a vector variable to be set to work. For that, we're going to need to set up a blackboard and create that variable. The blackboard is a place where we can store data to be used for decision-making purposes. They can be used by a single AI pawn, and some variables can actually be shared by a squad of AI entities. It can also be used with behavior trees, but behavior trees don't necessarily need to use blackboards to work. To create a blackboard, right-click the Counter browser, then find Artificial Intelligence Blackboard. Later on, set it as your blackboard on your behavior tree. After that, we will create a new key of type vector value. We're going to call it patrol location, and we're going to use it to store location data for this behavior. To write the value to our blackboard, we're going to create our first behavior tree task. Create a new blueprint object based on BT-task blueprint base. To implement logic when this task is executed, override the receive execute AI event. Let's start by adding a set vector parameter value, and let's promote the blackboard key in this function to a variable. We're calling blackboard key. Let's add a random location node. Let's set the origin to the control pawn location or the AI entity location. And don't forget to make the radius of that random node a variable too. Both radius and the blackboard key variables, they have to be marked as public and visible, so we can change them later in the behavior tree. After we compile and save, we can see that our new task, getRandomLocation, is already on the list, and that we can also customize those variables. We're going to set our blackboard key as the patrol location. But if we play the game, you see that task getRandomLocation is actually never finishing the execution. And the reason for that is that every behavior tree task has to finish with a failure or success condition, so the behavior tree can control the flow of the execution of the other tasks in that branch. So now we're finally good to go. You can see that our enemy is finally patrolling the area, picking a random location around itself every time the behavior tree cycles. We're going to call this our patrol behavior. Let's now add another behavior to our AI. We've mentioned before that selector nodes behave differently and that you can use them when you need to pick a single branch to execute. And if we play the game, our selector node would just pick its first child. But what if we add a higher priority child with a valid task? Well, it will only select that branch. And I know I'm risking being repetitive here, but that's really what selector nodes do. So as we said before, the selector node would try to pick the first branch that doesn't fail. So what we really need here is that this first branch to fail, given a certain condition. For that, we're going to use a decorator node. And the decorator node we're using is the Blackboard-based condition. It checks if a Blackboard key is valid. For this behavior, we're going to create a new Blackboard key called target actor. We're also going to set it as an actor so we can reuse its location in other parts of our behavior tree. In our decorator node, we're now going to select our target actor. And since that target actor was never set, that conditional will always fail. So the selector node now picks the next child. And now we will be able to switch between these different branches by setting that Blackboard key using the perception system. The AI perception system provides a way for pawns to receive data from the environment, such as where noises are coming from, or if the AI was damaged by something, or even if the AI sees something. This is accomplished with the AI perception component that acts as a generic stimuli listener and is able to gather stimuli from other actors. Let's now open our enemy AI controller and then add an AI perception component. Inside that, we're going to add a new sense. We're going to use the AI site config and then configure our sense, site radius, and the angle. We're going to do some workaround. We're going to have to select all these items because the detection by affiliation feature is not currently exposed on blueprints. And the last workaround is to edit the config defaultgame.ini and add these two lines to make sure that only the pawns we want will be detected by the perception system. And the reason for that is that we want to select those actors manually. For this, we're going to use this component, the AI perception stimuli source. And then we're going to add the senses that we want the perception system to detect in this actor. So let's now get back to our enemy AI controller. And then on our AI perception component, we're going to use the onTarget perception updated event. Then we're going to get our Blackboard and set value as an object. So the Blackboard key name we want to write to is the target actor. And the object value is going to be the actor we have just detected. Let's get back to our behavior tree and do a few things. Let's change the wait time. Let's add a move to the target actor. And a really nice feature is that you can actually rename those nodes to something that makes more sense for later reference. Our enemy pawn is pre-configured with a blueprint interface that uses an enum to switch between different states: neutral, investigating, and alerted. This changes the lighting effects, colors, and serves as a visual cue to the player. To be able to change that from the behavior tree, we're also going to create a new behavior tree task that calls that same function using a blueprint interface. And now, you just need to add that new task to the branch and select the proper state for that behavior. We have now covered most of the features of Unreal's AI framework, so let's now talk about debugging. Unreal comes with a built-in visual debugger for AI features. So let's check that. To show the gameplay debugger UI, press the tile key during play. You may have to configure another key in the project settings, then gameplay debugger. Make sure you select a key that works for your keyboard. The gameplay debugger presents this UI overlay with information about your enemy pawns and AI controllers, including information from the perception system and the behavior trees. You can change between different modes by pressing the numpad keys on your keyboard. You can also press Tab to decouple from your player pawn and fly around like a spectator pawn. Let's try the Perception System debug mode. You can see that it shows the enemy sight radius and angle, and we are able to see if the player has been detected or not, represented by this green sphere. If you pay attention, even though our player is in the detection area, it takes a few seconds for the behavior tree to be updated. And the reason for that is that the patrol branch is still being executed, even though the blackboard value was already set by the perception system. We can fix this by selecting the proper abort mode in the decorator node. Some decorator nodes can force the end of the execution of itself, abort lower priority branches, or even both. In this case, we will set it to abort everything and reevaluate the behavior tree from the root. And now, as soon as we enter the sight detection area of our enemy, our behavior tree is reevaluated and the right branch is picked almost instantly, getting the AI in the desired alert state. Let's now add another behavior to our enemy AI. We want our enemy to be alerted of noises close by and head to that location to investigate it. First, let's create a new vector blackboard key called target location. Then, we're going to copy and paste the blackboard decorator node and change the blackboard key to the target location key that we have just created. Let's copy and paste some of the other tasks. Let's set the alert state to investigate. We're going to add a move to node to our target location, add another wait task, and we should be good to go. We're now going to create yet another behavior tree task to clear a blackboard value when we need. We're going to use the clear blackboard value node for that. Just finish it exactly like we did before. Back to our behavior tree, let's add the task we have just made and clear the target location blackboard value. We now just need to make sure that the actor who's going to trigger the hearing sense has the AI perception stimuli source component and that it has the proper senses registered as a stimuli. Here, we're going to detect when this actor hits a surface for the first time and then trigger a noise event using the report noise event method. Let's now head back to our enemy AI controller. We will need to make a change to our target perception event. We will need to check if the stimulus type of a given event is of type AI sight and treat it correctly. For the sake of simplicity, let's leave the target actor blackboard key as the conditional for our sight sense. And if it's not a sight detection, then we're going to assume it's a hearing stimuli. And if it is, then we're going to set the blackboard key target location to a vector. And that vector is going to be the actual location the perception system detected, the stimulus location. Now we just need to make sure that our perception system is able to detect noises too. And we're adding an AI hearing config to it, changing some of its data and do the same workarounds that we did before with the AI sight config. And if we play our game, we can now distract our enemy AI with noises, moving it out of our way, at least temporarily. Our enemy is able to randomly patrol areas around, but its movement is not really that smart. Since it's completely random, it can get stuck in areas or sometimes just be facing a wall indefinitely. We're going to improve this by making our AI aware of the environment, and for that, we're going to use the environment query system. The environment query system allows an AI entity to query the environment, or the level, and get usable data from it. EQS queries can be used to instruct AI characters to find the best possible location that maybe provide a line of sight to attack a player, or the closest health pickup. It's very useful when you need to make important decisions that need an understanding of the environment around the AI entity. Before we start, let's make sure we have EQS enabled. Go to Settings, Plugins, and then look for the Environment Query plugin. We're now going to improve our patrol routine by changing the way we pick the patrol point. Let's replace this task with an EQS query. Let's then create a new environment query, select the proper folder, and give it a name. Double-click to open it. And dragging off the root, you can see we have different kinds of generators we can use. We're going to select the cone generator, and then we're going to set its cone degrees to 200. Let's play the game and quickly get into the gameplay debugger mode and press 3 to enable the EQS debug system. What we can see here is that the EQS query is generating this cone in front of the enemy and picking a single position. That's going to be set as the patrol location, which is going to be used by our behavior. Let's make it a little bit smarter by adding a distance test. We're going to leave it as filter and score. We're going to test the distance to the querier or the actor, and we're going to set the filter type to minimum. What it's going to do, it's going to give a higher score to the points that are farther from the querier. And now we can see that the EQS query not only generates these points, but also is giving a score to each of these. In this case, based on the distance to the carrier. The farther, the higher the score. Let's now add an overlap test. We're going to set this as a filter-only test. We're going to change the overlap shape to a sphere. The radius is going to be 75 centimeters, and we're going to add an offset so it doesn't hit the ground. And what we can see is that our overlap check is filtering out every point that does not collide with a wall because of the offset that we added. But what we really want is the inverse condition. So we're going to disable the bool match, and that's going to give us the inverse condition. It's going to filter out all the points that are barely touching the walls, giving us a much clearer path, a path that seems more natural. Let's add yet another test. That's going to be a dot test that checks the angle from the querier to the actual item that's been evaluated. And what it does is scoring higher the points that are in front of the querier. And now our EQS query is trying to select the farthest point that is the most perpendicular to the enemy direction. We can change that adjusting the scoring factor of the tests. We're going to change the rotation weight to 0.25 and the distance weight to 0.75, basically normalizing the scores of these two tests. And now that we changed the scoring factors of these tests, our EQS query will do its best to select the farthest point in front of the enemy. But because the distance test has a bigger weight, it takes precedence, and in cases like this, it will allow the enemy to turn when it faces a wall. Using the gameplay debugger is not always ideal to test EQS queries. For that, Unreal has the EQS testing pawn. It's an actor type that you can add to the world and select an EQS query and visualize it live. It's very useful to fine-tune values or test the query in different locations. You can also select the data you want to see, like the test result labels, or filter the points that fail and highlight the ones that the query will probably pick during gameplay. Everything is live, and it's right in the editor. Let's now try another example by adding a subroutine to our investigate behavior. After the enemy moves to the target location to investigating a noise, we're going to run an EQS query to find places that the player may be hiding, and do it 3 times using a loop decorator. Our EQS query consists of a cone generator with an angle of 360 degrees. We do a dot test to check the angle of the point, but here we use a negative scoring factor to give it a higher chance to select the point behind the enemy. And this is the most important one. We're doing a trace test to check if the enemy has a line of sight to the point. In this case, we're going to filter the points that test positive and have no line of sight, or the ones that are actually hidden behind walls. To finish that, we're going to add a distance test to get the points with the higher distance. Using our EQS testing pawn, we can see what this query does. It's actually trying to select the points behind the enemy, but it only considers the ones that are currently hidden, that the enemy has no line of sight. And this kind of query can be used in other situations, like when the enemy needs line of sight to the player, or when it needs to find the best point to take cover from it. As we can see, during the investigation routine, the enemy now tries to look for possible locations where the player could be hidden, adding this interesting level of intelligence to our AI behaviors. And here we conclude this video. We have covered from the basics of how behavior trees work, to how to make your AI entities react to events using the AI perception. We've also learned how to organize different behaviors in your game, and finally, the basics and some advanced EQS queries to make your AI smarter about the environment. I hope you have learned a lot about the Unreal Engine's AI framework today. Thanks for the audience, and goodbye.